All righty, friends. How are we all doing today? Good to see you guys. We're going to continue working our way through this idea of series and sequences, and we're going to kind of go into a different type of thing just for a day, and then we're going to tie it all together. There's a way that they end up tying together. So this next kind of idea is more of an analysis type of idea. It's called counting. It's the mathematics of counting. How many ways can you do something? This is also related to probability, which we're not going to get into. You guys did a lot of probability back in integrated 2. But it's just a way to determine how many ways things can be ordered. The item that we're going to use a lot that kind of governs this whole idea here is this thing called the fundamental counting principle. Some people call it the multiplication counting rule, and some people call it the multiplication counting principle. Technically, it's the fundamental counting principle, and it basically says however many ways something can happen, when you combine that with other things happening, you just multiply them all together. In other words, we multiply all the outcomes for each event together to figure out how many different ways in items we can create. So for instance, say I have water or iced tea, and I'm gonna eat a veggie burger, a hamburger, or a cheeseburger. How many different types of meals can I make? 2 drinks, 3 types of burgers, 2 times 3, there are 6, so 6 meals. And what we're gonna look at today is we're gonna look at the idea of determining how many ways things can happen. So let's take a look at this first one. We have a bag that contains 12 tiles, all numbered 1 through 12. How many ways can we choose 3 tiles if the chosen tile is replaced after each drawing? So in other words, we're going to choose 3 tiles. We don't know what those tiles are. We don't care. All we know is that we're going to be choosing 3 tiles. So when we take out one of the tiles, take it out, there's 12 different tiles I could possibly take out. So we don't know which tile it is, but we know that there's 12 different tiles. So how many different tiles can I choose for the first item? There's 12 different tiles, so I have 12 tiles to choose from. And then notice, the item is put back. The tile is put back. So on my second drawing, how many tiles can I choose? Well, there's 12 because we put it back. All right, so we come back to it again. We put our tile back. Our third drawing, there's 12 tiles again, it's still in the bag because there's 12 for us to choose from. So we have 12 tiles to choose. So how many different combinations can we make? Well, just the fundamental counting principle says multiply them all together. So 12 times 12 times 12 would be 1728. All right, why don't you guys try part B here if we don't replace the tiles after selecting. Go and pause the video and let's see what you come up with. All right, let's see how you did. So the first time you select, there are 12 tiles. But this time we don't put the tiles back. So the next time you select, there are 11 tiles. Don't put either of the 2 tiles back, and now you're down to 10 tiles to choose from on the first one. So think of it this way. If we have all of our numbers here of 1, 2, 3, 4, 5, 6, 7, 7, 8, 9, 10, 11, 12. So the first time we draw, if we're not replacing, we had 12 tiles to choose from. And then we took out a tile, so say we chose 7. Now the second drawing, we have 11 tiles to choose from. Don't put it back. In the last drawing, we have 10 tiles to choose from. That's what's going on here, okay? So when we plug that in, we end up that there are 1,320 different ways to combine those 12 tiles in groups of 3. So we're just going to continue playing with this idea of the counting principle here. There we go. And let's see, why don't you guys go and pause the video and see how you do with all these different ideas, and then we'll come back and talk about it. All right, so right here, we had 4 shoes. We had 3 pairs of pants. We had 5 different shirts. And we had 2 hats. How many different ways can we go about making up these different orders? So we have 4 different events take place here. And so we had 4 pairs of shoes, 3 pairs of pants. Oopsies. We had 5 shirts. And we had 2 different hats. And if we put them all together and we multiply, we would have 120 different outfits. So somebody going, oh, I don't have enough clothes. You got plenty of clothes, friends. You don't need to be doing anything else here. Now, this one's kind of like our tile problem we had before. So we have 3 different ways to pull out 26 tiles. So first choice, we had 26. And the letters can be repeated. So 26 and 26. And all together, when we multiply it all the way out, we end up with 17,576. Sometimes students have problems with this because they look at all these different possible outcomes and they're going, there's so many different things it could be. And I get that. It's just remember that it is enormous. It's vast, but it still logically makes sense. Right? It's just sometimes hard to wrap our head around it. So we had 26. This time they can't be repeated. So I use up one of my letters. So now I have 25 letters left. I've used up 2 letters. So that means I have 24 letters left on the third try. Multiply it all the way out in 15,600. And some people really enjoy these. Some people think these are a lot of fun. Some of y'all, you won't necessarily enjoy it all that much. So we have this last one. Telephone numbers are made up of a 3-digit area code followed by a 7-digit local number. If the first 2 digits of the local number cannot be 0 and 1. All right, so they can't be, first 2 digits can't be 0 and 1 of the local number. That's the important part, the local number. How many different local numbers can be created? So we're not dealing with the area code. We just want the local number. So here we go. I have a 7-digit number. 1, 2, 3, 4, 5, 6, 7. Oh, I got 1, 2 in there, don't I? So I have a 7-digit number. Now, when you're looking at this here now, realize how many digits do we have? A lot of people always want to come out and say, oh, well, there's 9 numbers, 1 through 9, but they forget that 0 is a digit as well. 6, 7, 8, 9. So this first one, it says, hey, you can't use 0 and you can't use 1 as your first number. So how many digits would you have left? Well, you'd have 8. So we can go ahead and we put 8 in here. After that, it doesn't matter how many numbers you have left. You can use any one you want. So that means we have 10 here, 10 here, 10 here, 10 here, and we're just going to keep multiplying all the way down. 10 here and 10 here. Multiply, multiply, multiply. We're going to multiply it all the way out. How many 7-digit numbers could we possibly make? Well, we'd make 8 million. It's kind of weird to think about. There's around 8 million different phone numbers we can make. Now, there's other restrictions that would go into it in real life. Like, for instance, you can't have 911 be the first 3 digits either. That would be bad. There's other things that you can't have, but for the most part, this is kind of the gist of how it works. So the next thing we're going to get into is other ways to order things. And the way we're going to order things is with something called a permutation. So now a permutation, and I can't stress this enough, a permutation is when order matters. Order matters. In other words, when I'm grouping things together, if order matters, A and B is a different permutation than B and A. They're different. It deals with specific things. It doesn't matter that they're still the same two things in the same group. It's that order matters. Now, if you notice, we have a little formula to determine how many different ways things are ordered, and that's called N permutate R, NPR. All right, NPR, and then we have this formula of N factorial, N minus R factorial. Now, N is how many items we get to choose from. See, this is the total number of items. And R is how many we want. So if we're looking at this here, friends, we're looking at this here, we're going to be plugging numbers in to order. So let's take a look at number one. It says 8 runners were competing. So we have 8 total runners. So that means N is 8. 8 runners were competing. How many ways could the 8 runners finish in the top 3 places? So we have 8, but we're trying to figure out how many ways to order 3. So this would be then order matters, because if you finish first place, that's not the same thing as you finishing second place, third place. It's like you'd rather have a gold medal than a bronze medal. So this would be a permutation because order matters. When order matters, it's a permutation. So 8 permutate 3. So that's 8 factorial all over 8 minus 3 factorial. So 8 factorial over 5 factorial. And let's remember what factorial is. That's where you count from 1 all the way up to your number, and you multiply them all together. So 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 all over 1 times 2 times 3 times 4 times 5. And whatever they have the same, no, that's what we can cancel out. So notice I have a 1, 2, 3, 4, 5 here. So I can cancel that out with the 1, 2, 3, 4, 5 here. So what I'm really left with then, the number of ways to do this is 6 times 7 times 8, which is 336. Now, for some of you guys, you are wanting to use your technology, your graphing calculators, and I get that. So let me show you where that would be on your graphing calculator. First thing I want you guys to do is I want you to go and find the button that says Math. And when you click the button that says Math, 4 things pop up. You have Math, you have Num, N-U-N, you have CPX. These all carry different weights and mean different things. And we have PRB. I'm going to guess that you might be able to figure out what PRB stands for. That's where we're going. It stands for probability. So number one, you have something called random when you do it, but we won't ever use random. What we're going to use in this section is this part right here, NPR. And by the way, in number 3, you have NCR. We'll use that in a second. And then number 4, like we talked about in class, you have your exclamation point. That's where your factorial button is. So if I wanted to type this into my calculator, I would do 8. And then I'd go find my NPR button. And when I click on the NPR, it's going to say NPR. And then I would type in 3. So that's what you're telling the calculator is you're going to plug 8 in for the N value, and you're going to plug 3 in for the R value, and your calculator will go ahead and do this for you. And it will tell you that's 336. So why don't you guys take a second here, pause the video, see what you can do with this next one. Yep. All right, let's see how you did. You have 8 textbooks. So we have our n value is 8. How many ways could you arrange all 8 of your textbooks? Arrange all 8 of your textbooks. Order matters. Order matters. So I have 8, and I'm going to arrange it by 8. So 8, P, 8. And we plug this in here, 8 over 8 minus 8. And I know what's going to happen here. I can hear it. Wait a minute, you can't divide by 0. But friends, this isn't 0. This is 0 factorial. Factorial is means arrangements. Okay, so dealing with arrangements. How many ways can you arrange nothing? Well, you have one way to arrange nothing, and that is nothing. So by definition, we say that 0 factorial is always equal to 1. All right? 0 factorial is always equal to 1. So 8 factorial divided by 0 factorial. So now when you guys are doing this on your homework, once you've gone ahead and done that, you can actually tell me the answer. All right, so you don't necessarily need to show all the work behind it, but you just need to show me the answer. So 8 factorial, that would be 40,320 ways, which is crazy. You have 8 classes, you have 8 books. You can arrange them in that many different unique arrangements. It's crazy to think about. So let's keep going a little bit. There we are. A local company is hiring extra summer help. It needs 3 additional workers on the loading dock and 4 additional workers in the warehouse. How many ways can the positions be filled when there are 11 applicants for the loading dock and 8 applicants for the warehouse? All right, go ahead and pause the video and see what you guys can do with that. All right, so let's see here. I have 3 workers that I want for the loading dock, and altogether I had 11 applicants. I wanted 4 workers in the warehouse, and altogether I had 8 applicants. But notice I got 2 different events going on here. I got one for the loading dock, and I got one for the warehouse. So I have 11 applicants for the loading dock, and I wanted 3 of them. So N is 11, and I wanted 3 of them. In the other one, I had 8 applicants in the warehouse, and I wanted 4 of them. So I also have going on here 8 P 4. These are 2 different events. And if I have 2 different events, then that means the multiplication counting principle says I need to multiply them all together. So I have a loading dock event going on here. 11 minus 3 factorial. And I had a warehouse event going on here. So 8 factorial, 8 minus 4. So again, once you're here, you need to show me that you simplify it out a little bit. So 11 factorial over 8 factorial times 8 factorial. Well, notice I got an 8 factorial on the top and on the bottom. Those could cancel out when I'm multiplying fractions. Over 4 factorial. So altogether I have, when I put this in, and this is where you get some of these crazy numbers, I have 1,663,000 if these were specific roles. If these were specific roles. If they were specific roles. Now, friends, here's my question for you. This is if Each of these positions were a specific role. Specific position, a unique position. If they aren't a unique position and it's the same thing, one loading dock worker is the same as another loading dock worker, that's when order doesn't matter, all right? And if that's the case, this is not a permutation. It would be something that we're going to get to in a second called a combination. So this one is if these positions are all specific positions. Now, if they're not specific positions, that's what we're going to get to in a second. If they're not specific positions, it would not be a permutation. If they're not specific positions, it's not going to be a permutation. It'll be something that we call a combination. So we're going to come back to this one in a second and look at what would happen if they aren't specific. So hang on to that. We'll be back here in a sec. Now, we keep going here, friends. Sometimes you have permutations where things repeat. Like, how many ways can you arrange the letters in Mississippi? Well, friends, you got 4 S's and 4 I's and 2 P's. It doesn't matter where I put a P. Those P's can be the same thing. So they're not different letters. It's the same thing. And that's what this little formula says up here. Each thing that it repeats, however many times it repeats, that goes in the denominator. The total number of terms would go on top. So let's take a look at this here. If I were to look at this, I have 11 letters. So that means I have N equals 11. And then I'm looking at each individual letter and say, okay, what letters repeat? Well, M doesn't repeat. I can forget about that one. But I does repeat. I have 4 of them. S repeats. I have 4 of those. And P repeats. I have 2 of those. So if I wanted to look at this problem here, I'd have 11 factorial divided by all these repeating numbers. 4 factorial, 4 factorial, and 2 factorial. And when we do that there, friends, we plug that into our calculator here, we end up with 34,650. Another way to look at this is 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10 times 11 and 4 factorial. 1 times 2 times 3 times 4. And then we have another 4 factorial. 1 times 2 times 3 times 4. And then we had a 2 factorial. 1 times 2. And if we were to simplify this, another way to look at it is we could go through and just start crossing off terms that are same. So 1 times 2 times 3 is the same thing as 6. 4 times 1 times 2 is the same thing as 8. What we really are looking at here then is 5 times 7 times 9 times 10 times 11. And you still get the same answer if you do it that way. Let's try this one. California. How many letters are there? California. I'm told they know how to party. Hopefully they can do math as well. We have 10 of them, it looks like. And let's see here. What letters repeat? A repeats. We have 2 of those. And I repeats. We have 2 of those. So if that's the case there, then this would end up being 10 factorial over 2 factorial over 2 factorial. Even though there's more letters in Mississippi, notice there's a lot more ways to represent the letters in California than there are in Mississippi because there's less letters that repeat. That's called a distinguishable permutations. The last thing we're going to look at today is something called a combination. Now, a combination is when order doesn't matter. Order doesn't matter. Look, it's very similar to a permutation. If you notice, here's our permutation formula. It's just we have an extra r factorial in the denominator. So we're going to try these two, and then we're going to go back and take a look at that problem we had before with the dock workers and the warehouse workers. Because what if those were the same position and just they needed people to fill them and they weren't unique roles? So we'll go back and take a look at that here in a second. For a certain experiment, 5 students are selected randomly. So we're going to select 5 from a class of 25. And then how do you know that we are dealing with a combination? Because we're dealing with groups. Friends, in groups, it doesn't matter what group you have, as long as they're all mixed up together. Think of it as a pizza. I don't care how the ingredients of a pizza are put on. Friends, I'm going to eat it. Stomach is going to enjoy it. And the way my stomach's going, maybe enjoying it too much. So we have 25 C5. So 25 factorial over 25 minus 5 factorial. And we can plug this into our calculator the same way we did the NPR. NCR is literally right below it. So you can do it the same way. I would want to see you simplify this a little bit more though before you go to your calculator. You always have to type it in or write it like this. And once it's simplified here, then you can use your calculator to go ahead and crank out the answer for you. But I want to make sure that you guys show me that you know how many different ways you can do it and what the arithmetic is behind it. Okay. And how many ways can we, well, why don't you guys go ahead and pause it and try this next one on yourself, by yourself. Okay. How many ways can we group? There's our combination word right there. 3 letters. So we're going to be dealing with 3 chosen from the letters in a wildcat. Well, there are 8 letters in a wildcats. Well, first of all, we have probably over 2,100 wildcats here at the school, but that's another story in general. So we have 8 C5. So 8 factorial over 8 minus 3 factorial times 3 factorial. So 8 factorial over 5 factorial, 3 factorial. So once you go ahead and simplify it down, now you can use your calculator to go ahead and tell you the answer. And there's 56 ways to get 3 groups from wildcats. All right, so now let's go back to that question we had earlier. I don't think these positions in the warehouse and the loading dock, I don't think that they're actually any different. I think they are interchangeable. In which case, if they're interchangeable, then order wouldn't matter how you select them. It would just be that you would have a team of loading dock workers you're selecting. You'd have a team of additional warehouse workers you're selecting. If order doesn't matter, so in this time we're going to say order doesn't matter, because I believe this is what this is. I believe this is one where order doesn't matter. Order doesn't matter on this, like this one really doesn't really matter. This would be then a combination. So this problem in general is actually a combination. We're not filling specific roles on the loading dock or specific roles in the warehouse. If we were, it'd be a permutation, but we're not filling those specific roles. If we were just creating a team of additional workers, which I believe is what we're doing here, then this would become a combination problem, not a permutation problem. If order doesn't matter and we're just creating groups, then instead of being NPR, now we're going to be doing NCR. CR, because order doesn't matter. NCR, or so 11C3 for the loading dock, 8C4 for the warehouses. So they're not filling specific roles. This would be they are actually filling a team that they can choose from, so they have those additional workers. So 11 minus 3. Times 8C4. And that ends up being 11 factorial over 8 factorial. Kind of looks like my factorial got lost in there, didn't it? 3 factorial and 8 factorial. 5 factorial, 4 factorial. All right, go ahead and take a second here. Plug that into your calculator, the Explorer, and let's see what we get here. So, oopsies, I plugged it wrong into my calculator. 11C3 times 8C4. And we end up with 11,550 ways to do it. Notice, this time, order didn't matter. Order didn't matter. We weren't filling specific roles. We were just creating a squad of extra workers. It's a lot smaller number than we had before. When order did matter, we said that this would have had 907,200 positions. If dock worker 1 was different than dock worker 2, which is different than dock worker 3. But if order doesn't matter and it's just a group of 3 dock workers, notice how much smaller that is. So on this problem, this would be a combination. Order didn't matter. 11,550 ways. All right, friends. So give you guys some things to think about. We'll talk more about this tomorrow in class. So have a great day.